I welcome you all in our today's session. In the previous video, we have seen how to find out or how to determine the order of the Butterworth filter. Now, based on that, we are going to see how to find out the order for the given Butterworth filter provided some specifications of the analog filter. Here, in our example, given the specifications are alpha p is equivalent to 1 dB, alpha s is equivalent to 30 dB, ohm p is provided as 200 radians per second and ohm s is provided as 600 radian per second, and we have to determine the order of the Butterworth filter. Now, as we have discussed in our earlier session, the order of the Butterworth filter is given as n is equivalent to n should be greater than or equivalent to log of a divided by log of 1 by k. So firstly, we have to determine the value of a and we have to determine the value of k. So what is a? A is equivalent to lambda divided by epsilon. Substitute the values here. Lambda is 10 raised to 0.1 alpha s minus 1 divided by 10 raised to 0.1 alpha p minus 1, the whole raised to 1/2. Substitute the values here. Alpha s is provided, also alpha p is provided. So 10 raised to 0.1 multiplied by alpha s is 30 minus 1 divided by 10 raised to 0.1 into 1 minus 1 raised to 1/2 or 0.5. So it will be 10 raised to 3 minus 1 divided by 10 raised to 0.1 minus 1, the whole raised to 0.5. This value after calculation is 62.115. So this is our A. Now what we have to do? We have to find out the value of K. So K is given as ohm P divided by ohm S. Ohm P is provided, that is 200 radians per second, while ohm S is equivalent to 600 radians per second. So after simplification, it will be 1 by 3. Now substitute these values in the equation of n. So it will be n is greater than or equivalent to log of a divided by log of 1 by k. So it will become greater than or equivalent to log of 62.115 divided by log of 3. So it should be greater than or equivalent to 3.758. So we have to select the order of the filter greater than 3.758. So round off, after round off, the n is equivalent to 4. So order of the given Butterworth filter is equal to 4. So in this way, we can calculate the order of the given filter from the provided analog filter parameters. We will see one more example to determine the order of the filter. So here one more example is provided. What we have to do? We have to determine the order and the poles of the Lowpass Butterworth filter that has a 3 dB attenuation at 500 Hz and an attenuation of 40 dB at 1000 Hz. So what is our given data? Here the alpha p is provided, that is passband attenuation, it is 3 dB. Also alpha s is provided, that is stop band attenuation, it is 40 dB. Ohm P is provided, which is at 500 Hz. We have to convert it into radians per second, so it will be 2 pi into 500, which is 1000 radians per second. In the similar manner, we have to find out ohm S, which is 2 pi into 1000, which is 2000 pi radians per second. Okay. Now, in the similar manner, we have to find out n here. So, what is n? According to the equation, n is given as log of a divided by log of 1 upon k. Okay. So, substituting these values here, log of square root of 10 raised to 0.1 alpha s minus 1 divided by 10 raised to 0.1 alpha p minus 1, the whole divided by log of ohm s divided by ohm p. Okay, so it should be greater than or equivalent to log of square root of, after substituting these values, we have 10 raised to 4 minus 1 divided by 10 raised to 0.3 minus 1, the whole divided by log of 2000 pi divided by 1000 pi. So after solving this, we have n should be greater than or equivalent to 6.6. So round off to the nearest higher value, we have n should be equivalent to 7. Now we have to find out the poles of the Butterworth filter. How to find out? Sk is given as ohm C into e raised to j phi k. Okay, so here we have to find out the values of phi k. Phi k is equivalent to pi by 2 plus 2k minus 1 into pi divided by 2n, where k varies from 1 to 7. So substituting these values here, we have to find out phi k, and accordingly we have to find out the different values of sk by substituting the values of k here. Okay, so in this way we can find out the poles of the given Butterworth filter. Okay, now I hope you have an idea now how to find out the order of the given Butterworth filter. Okay, now we are going to see the different steps to design an analog Butterworth low pass filter. Okay, so what are the steps to design an analog Butterworth filter? Okay, so firstly what we have to do, from the given specifications we have to find out the order of the filter. Okay, so from the given specifications find the order of the filter, that is n. So what is the equation for n? N should be greater than or equivalent to log of square root of 10 raised to 0.1 alpha s minus 1 divided by 10 raised to 0.1 alpha p minus 1, the whole divided by log of ohm s divided by ohm p. Okay, so by using this equation, firstly we have to find out the order of the given filter. Now what we have to do, we have to round off n to the next higher integer. That is the order of our filter now. Nextly, what we have to do, we have to find out the transfer function h of s. Okay, so find out h of s for Ohm C is equivalent to 1 radian per second. How to find out H of S? We have seen earlier. We have to consider the poles which lie in the left half plane. Okay, and by using those poles, we have to determine the denominator of H of S. Okay, so by considering that denominator, we have to derive H of S for the given value of N. Okay, in our earlier video, we have seen this. Now calculate the value of cutoff frequency. Actual cutoff frequency. Okay, so now keep in mind that this equation of H of S is for the normalized transfer function. Now we have to find out the transfer function for unnormalized system, okay, or unnormalized filter. So we have to firstly find out the actual value of cutoff frequency, that is Ohm C. Okay, now again we have to find out the transfer function HA of S for the above value of Ohm C by substituting S by Ohm C in the equation of normalized H of S. Okay, so wherever there is S, we have to replace it by S by Ohm C and simplify it. So we will obtain the transfer function for the given analog filter. Okay, so we will see one example so that we will all have an idea that how to design the analog Butterworth low pass filter. Okay, so here we will consider one example for designing an analog Butterworth low pass filter. Okay, consider here the alpha P is provided, that is alpha P is equivalent to 2 dB. Okay, alpha S is equivalent to 10 dB. Okay, Ohm P is provided, that is equivalent to 20 radians per second. Okay, and Ohm S is provided, that is equivalent to 30 radians per second. Okay, so we have to design an analog Butterworth filter. So what is our first step? First step is nothing but we have to find out the order of the analog filter. Okay, so first step is to find out N. Okay, so by using the equation, we will firstly find out N. N is equivalent to log of square root of 10 raised to 0.1 alpha S minus 1 divided by 10 raised to 0.1 alpha P minus 1, the whole divided by log of Ohm S divided by Ohm P. Replace the values, we will have log of square root of 10 minus 1 divided by 10 raised to 0.2 minus 1, the whole divided by log of 30 divided by 20. So after solving this, we have N should be greater than or equivalent to 3.37. Okay, so we have now the value of N. So what is our second step? We have to round off the N to the next higher integer. Okay, so we have to round off it to next higher integer, that is equivalent to 4. This is our second step. Now what is our third step? We have to find out the transfer function H of S for the given order of the filter. Okay, so according to this, we have to firstly find out S1 to S4 values. Okay, and then we have to find out that means we have to firstly find out the poles of the given function. Okay, and then we have to consider the left half poles. So this value or the transfer function for n is equivalent to 4 we have described in our earlier video. In that case, we have derived the h of s is equivalent to 1 divided by s square plus 0.76537s plus 1 into s square plus 1.8477s plus 1. Okay, this is the transfer function for the Butterworth filter for the order n is equivalent to 4. Okay, so this is the case when Ohm C is equivalent to 1. Okay, this is our third step, that we have to find out the transfer function for the given order of the filter at Ohm C is equivalent to 1 radian per second. Okay, now what is our next step? Next step is we have to find out the actual Ohm C cutoff frequency. Okay, the equation of Ohm C is Ohm P divided by 10 raised to 0.1 alpha P minus 1 raised to 1 divided by 2 n. Replace the values here. Ohm P is provided, that is 20 divided by 10 raised to 0.1 into 2, that is 0.2 minus 1 the whole raised to 1 divided by 4 into 2, that is 8. So solving this, we have now Ohm C is equivalent to 21.3868. Okay, so this is our actual cutoff frequency. Now what is our fifth step, that is last step? Okay, to find out the actual transfer function, we have to substitute S by S divided by Ohm C. That is, we have to substitute S by S divided by 21.3868 in H of S. So in this equation, wherever there is S, we have to replace this value. Okay, so what is our H of S now? Our new H of S is equivalent to 1 divided by S divided by 21.3868 raised to 2 plus 0.76537 into S divided by 21.3868 plus 1 multiplied by 1 divided by S divided by 21.3868 bracket square plus 1.8477 into S divided by 21.3868 plus 1. So after simplification, we have H of S is equal to 0.20921 into 10 raised to 6 divided by S square plus 16.3686s plus 457.394 multiplied by S square plus 395176s plus 457.394. Okay, so this is our transfer function for the provided but analog Butterworth low pass filter. So we have followed all the 5 steps here. Okay, so I hope you understand how to design an analog Butterworth filter from the given specifications. This section will be helpful for you for designing the digital Butterworth low pass filter. Thank you.